Right. So today we are going to discuss about elimination reactions, and since I'm in the lab, I might speak a little slowly, so don't mind. Okay. But this video is going to be important to understand the basics. So basically, what is happening in an elimination reaction is that two substituents are removed, like I've written over here, from a molecule. Okay. So for example, if we have sulfuric acid, so sulfuric acid dissociates into H plus and its conjugate base. Okay, this is the conjugate base. Now what happens is this H plus protonates this hydroxy group. Okay, this hydroxy group has lone pair of electrons. It attacks this H plus, gets protonated, and it leaves. Okay, now this step is the rate determining step because this is a slow step. Okay, then what happens is a carbocation is generated, like over here a secondary carbocation is generated, and then the conjugate base will abstract this proton and the acid will be regenerated. Okay, and we'll get this product. So this hydrogen will be abstracted, then this, like I've shown by the arrows, this bond, these electrons will shift over here and we'll have an alkene formed. Okay, now what is the difference? So if the nucleophiles are strong bases, they favor elimination. Okay, now I have seen a lot of students have this problem that what to take it as a nucleophile and what to take as a base. Okay, I mean, what is the difference between a nucleophile and a base? So I'll just give you an example. See, for example, with your mother you have a relationship of like a son, right? To your mother you are a son, and to your sister you are a brother, right? So to different people you have different relations. To your sister you are a brother, and to your mom you are a son. Okay, so similarly, but you are the same person, right? Even though you have a different relationship with different people, that does not change who you are. Similarly, a compound a molecule can be a nucleophile and the base, that is dependent on what is its relation. If it's attacking a hydrogen, then it's a base. If it's attacking a carbon, then it's a nucleophile. Okay, we'll look into that. So again, nucleophiles, I will take all the examples. Nucleophiles are bases that are bulky, favor elimination over substitution. So nu- um, why? Because bulky bases or bulky molecules would not like to uh, you know act as a nucleophile and attack the carbon, because there will be a lot of steric hindrance. It will prefer to take the hydrogen and leave. So that is why bulky bases favor elimination over substitution. And the third one is high temperatures favor elimination over substitution. So we'll look into these three mechanisms and then we'll have a look at the problems. So the three mechanisms that are followed are E1 mechanism, E2 mechanism, and E1cb mechanism. So in E1 reactions, rate determining step is unimolecular, and that is why it is known as E1 reaction, because the rate of the reaction is only dependent on only one kind of molecule, which is a starting material. Okay, this is a rate determining step because in E1 reactions you have to remember that first a carbocation is generated, like I have written over here. So the first step, or the rate determining step, or which is also the slow step, is what is first the leaving group, which I have denoted by X over here, first leaves, forms a carbocation, and then the base attacks the hydrogen. See, that's why I'm calling it a base, because it's attacking the hydrogen. Had it been attacking the carbon, it would have been a nucleophile. Okay, and we get the alkene, right? So this is the E1 reaction. It is a unimolecular reaction because it only depends on the rate of the reaction only depends on one molecule. Now let's look at the factors affecting. So more substituted halides react faster. Stability of carbocation. Basically what it means is a tertiary carbocation is more stable than a secondary, okay, and which is more stable than a primary. So a tertiary carbocation, if it is formed, will be more stable. That is the only meaning of more substituted. Substituted means more number of carbons attached. For example, in this case we had um, one and two carbons attached, so it was a a secondary carbocation was generated over here. If you see over here, this is a secondary carbocation. So secondary and tertiary carbocations, I mean tertiary carbocations will definitely give you E1 reactions. Okay, then it is favored by weak bases. So weak bases favor even reaction. Then presence of a very good leaving group or a better leaving group will also favor even reaction. And the fourth most important point is polar protic solvents. They are also stabilize the intermediate and lead to more favorable even reactions. Why? Because the carbocation generated over here will be stabilized by a protic solvent. Protic solvent is one which has a basically acidic hydrogen. Okay, any like OH bond, any solvent with a OH bond is called a protic solvent, or with a NH bond. Okay, these kind of solvents are polar protic solvents which have a OH bond or NH bond. So these kind of protic polar solvents stabilize the carbocation, which is why they favor the even reaction. Okay, now let's look at the which product is more stable. So we have a E alkene over here. If we take this kind of reactant, we add acid. So first again the acid will protonate the OH group, it will form OH2, and then water will leave and a carbocation will be generated. So what is happening? First the protonation is taking place. If you see this step, the protonation is taking place, then removal of water, and it is generating this carbocation over here, right? Now the water acts as a base in this case. So water can act as a nucleophile and it can also act as a base. Okay, so you cannot define whether a water is a nucleophile or a base. It is all dependent on how it is acting on that particular molecule. So over here it is acting as a base, so it will abstract the hydrogen from this compound, and it can give you two kinds of product. One is E alkene and one is Z alkene. These are the two products that are formed. Okay, but the E alkene is favored, or E alkene is formed faster, and that is why it is favored. Why? Because if you see the intermediate, see what is E and Z. E is basically the two groups, the two higher priority groups. That is, over here there is phenyl and over here there is methyl. They are in different planes or on the opposite sides. So then it is a E alkene. If they are on the same sides, then it is a Z alkene. Now if you see the intermediate, this is for the Z alkene intermediate and this is for the E alkene, the intermediate. Now in this case, because there is steric repulsions, if you see between this methyl and this phenyl, in this case there is steric repulsion between the phenyl and the methyl, because of which the intermediate is unstable and it is of higher energy. Okay, so the activation energy of this intermediate is very high. It is very high. Okay, so because of this it is not favored and our E alkene is formed. No doubt if you have a higher temperature, then this activation energy will be reached and then we can have this product as well, but at lower temperatures we'll have E alkene as the major product. Okay, now here is an example of E1 reaction. So this is a medicinal compound, tamoxifen, and this is the compound. To this we add the Grignard reagent, that is phenyl magnesium chloride, and this phenyl group attacks this. So basically it is existing as pH minus, right? So it is attacking this carbonyl carbon, and we are having a phenyl group over here and a OH generated. Now once we add the acid, now why are we adding the acid? Because OH is not a good leaving group. This OH is not a good leaving group, but once we add the acid, this acid protonates this OH to form OH2 positive oxonium ion, and this oxonium ion is a good leaving group. And being a good leaving group, this oxonium ion uh, is now becomes a good leaving group, and plus it's a tertiary carbocation. Right over here a tertiary carbocation will be formed, because if a carbocation is generated over here, once this OH2 group leaves, it will be a tertiary carbocation, and plus it will be stabilized by the resonance due to the two phenyl rings. So it is very stable, and hence it will favor even reaction to give us the product, and it will give us E alkene. So if you see over here, in this particular case it will give us these two products. One is E alkene and one is Z alkene, but the E alkene will be uh, more in quantity. I mean the ratio of E alkene to Z alkene, the E alkene will be the major product. Okay, And in this case, which is E alkene? See, we have this as the higher priority group, and this as the higher priority group. So this one is Z, and this one is E alkene. Okay, higher priority groups on the opposite side, because this phenyl is the higher priority group for this carbon, and this phenyl is the higher priority group for this carbon. Now, regioselectivity. What is the regioselectivity in such reactions? So major product is the more substituted alkene. Okay, what do I mean by more substituted alkene? Is the alkene where more number of methyl groups are attached. So for example, over here we have 3 methyl groups attached. If you consider this, we have only 2 methyl groups, only one methyl group attached, right? In this case we have 3 methyl groups attached. This is a more substituted alkene, and it is more stable. Okay, so first again the protonation takes place, then we have oxonium ion formed. This is known as the oxonium ion. So water is removed, we generate a carbocation. Okay, then this carbocation, this either this hydrogen can leave this one or this one. There are two ways by which the base can attack. Either it can attack this hydrogen or it can attack this hydrogen. But the more substituted alkene is formed faster. I mean, this hydrogen will leave to form a more substituted product. Okay, see, there I have drawn the intermediates, but I mean they're little difficult for you to understand, so I'm not explaining. And this is a very easy concept, that more substituted alkene is more stable. Okay, yeah. Now let's look into the E2 reaction. So as the name suggests, it depends on the concentration of the base as well as the starting material. So that is why, since it is a biomolecular reaction, it is known as E2 reaction. So basically, what the proton abstraction by the base, so this is the base, it abstracts the proton, and the leaving group, they both leave simultaneously. So that is why it is dependent on both the products. Now, factors affecting the E2 reaction. So more bulky alkyl halides undergo E2 elimination faster. Okay, so bulky halides undergo E2 elimination. Strong bases are required, like DBU and DBN. Okay, so strong bases favor E2 reaction. This is very important. Weak bases favor even reaction, and strong bases favor E2 reaction. Okay, polar aprotic solvents enhance the reaction rate. Basically, what is it is exactly the opposite of even reactions, and again, the better the leaving group, faster the reaction. Okay, so it is basically just the opposite, but in even reaction also, a good leaving group favors even reaction, and a good leaving group favors E2 reaction also. But a strong base will determine whether even reaction will take place or a E2 reaction will take place. For example, in this particular case, we have this very strong base. I have drawn the structure of that base over here. This is DBN. This base is called DBN. So it attacks this proton. Okay, this is the most acidic proton present, and then there is a simultaneous removal of the iodine group, and iodine is a very good leaving group. So this DBU base abstracts this proton, and this I group leaves to give us this product. Okay, okay. So again, in case of E2 reactions also, we have a E alkene being formed. Okay, and why is the E alkene formed? Because leaving group and proton should be anti-periplanar. Okay, now there's nothing difficult to understand over here. Anti-periplanar means they both are in different planes, or you can say, if I draw the hydrogen of this molecule, if I draw the hydrogen over here, this hydrogen and the leaving group, for example over here it's Br. So this hydrogen and this Br should be in opposite planes or at an angle of 180 degree. So in this case, that is why this is the major product, or the E alkene, because the higher priority groups are on the opposite sides. So that is why this is the major product E alkene. Now, why is the E alkene favored, or why should the proton and the leaving group be anti-periplanar? Well, it is all dependent on the molecular orbital theory. So I have to draw the molecular picture and then explain you why anti-periplanar is favored. But since I don't want to complicate things, so that is why, to keep it simple, I am not going into the orbital picture of E2 reactions. Okay, this is very important. Okay, so sorry for the wrong spelling. Setsef. This is spelling is wrong. Okay, so less substituted alkene is called the Huffman product, and more substituted alkene is called the Setsef product. Okay, I have drawn. I mean, spelling is totally incorrect. So sorry for that. Um, so these are two very famous there are four things that you should always remember. What is the anti-Markovnikov product, what is the Markovnikov product, what is a Hoffman product, and what is a Setsef product. These four things are very fundamental and you should know. Now why is this slide very important? Because if we use a sterically hindered base or a bulky base, then the Hoffman product is favored. Then the Hoffman product is formed, that is the less substituted alkene. Whereas if we use a less hindered product, okay, less hindered base, sorry, then we get a Setsef product, that is more substituted alkene. Now why does a bulky base like this tertiary butyl butoxide prefer prefer to form less substituted alkene? Now the reason for that is pretty simple, because a bulky base would not like to abstract a proton from this side. Okay, so this sodium ethoxide is basically abstracting a proton from this side, but a tertiary butoxide group will not like to abstract a proton from this side because of steric hindrance in this side, because of the two methyl groups or the two methyl groups. So this will try and abstract these protons which are free, where there's no hindrance, so it can easily go to this proton and abstract this. That is why the like I've shown over here in the mechanism, that this product is minor because there's steric hindrance, so this butoxide group cannot abstract the hydrogen over here. And that is why for bulky bases we have the Hoffman product, and um, for normal bases we have the Setsef product. Now these are E1cb reactions. Now E1cb reactions are nothing great about them. The concept is very simple, that when the anion that is formed is stabilized, then generally E1cb reaction is formed. So what I mean by that is, I'll just take an example and explain you. So we have this hydroxide. Okay, it acts as a base OH minus, right? KOH is basically existing as K plus and OH minus. So this OH minus is acting as a base. It abstracts this proton and then it forms O minus. Okay, so it abstracts the proton, forms O minus, and this is stabilized due to resonance. Okay, uh, so I mean, there is tautomerism, ketoenol tautomerism is taking place, right? And so basically because of this we are having, so the anion that is generated over here, the O minus anion that is generated, is being stabilized, and this is the most stable product, alpha beta unsaturated ketone. This alpha beta unsaturated ketone is more stable, and so this is formed. How is that formed? Basically we have, if I remove this H, we have OH, right? So this O minus, it reverts back. It's like I've shown over here with the arrow. This double bond moves towards this, and this OH minus leaves, okay, to form this product. Now I mean, elimination basically takes place, and since the O minus is stabilized, it is a E1cb reaction. I mean, it might not be clear now, but in the next slide it will get clearer. So let's move to the next slide. So these are some examples, and let's see what is happening and try and predict the product. Okay, so just pause the video now and try and figure out what could be the reaction and by which mechanism will it happen. So like I have told you, the slide is about elimination reaction, so obviously elimination reaction is going to take place, but you have to find out that what kind of elimination reaction is going to take place. whether it is E1, E2 or E1cb. Now if you see over here, if we use a base which is the most acidic proton present, the most acidic proton present is this proton over here. Why is this the most acidic proton? Because if a carbon ion is generated over here, so if I generate a carbocation over here, okay, if this base abstracts the proton, okay, then a carbon ion will be generated. I'm very sorry, a carbon ion will be generated. Now this carbon ion is stabilized due to resonance by the two phenyl rings. This carbon ion that is formed is stabilized by the two resonance due to the two phenyl rings. So it is a E1cb mechanism because the generated carbon ion is stabilized. So that is why it is a E1cb reaction. Now this group over here is a good leaving group. So what happens, this minus charge migrates like this and this group leaves to give us this product. Okay, what about this reaction? So sodium ethoxide. Now I told you sodium ethoxide is a non-bulky base. It is a non-bulky base. So what is it going to do? It will give us the more substituted product, right? It will give us the more substituted product. So so it has two hydrogens to abstract. Either it can abstract this hydrogen or it can abstract this hydrogen. Okay, but since it is a non-bulky base, it will abstract this hydrogen to give us more substituted product or the Seitzak product. So like you can see over here, we have got a ratio of 1:3 where the more substituted product is formed or is the major product. So this is the major product or the more substituted product. If we had used, for example, a bulky base like tertiary butoxide, had we used tertiary butoxide, for example, in this particular case, then what would have happened? This hydrogen would have been abstracted, and then this would have been the major product for bulky base. For a bulky base, this would have been a major product. Okay, right. What about this? Now this is a very good example, and I have taken this example from Claydon. So what is going to happen over here is, first, this we have acid. So this acid, instead of protonating OH first, it will protonate this group, OET group. Okay, because it has more electrons present, so it will protonate this. So we have H plus. Okay, we have H plus. This H plus will protonate this this oxygen will attack this H plus to form. I'll draw the whole thing. Again, an oxonium ion will be formed, right? Right. So now oxonium ion is formed. So now this becomes a very good leaving group. So the lone pair on this oxygen attack this carbon. This double bond migrates, okay, to oxygen, comes back, and then this group leaves. So basically we have ethanol as a byproduct, ETOH as a byproduct, and now what is formed is a 5-membered ring. So 1, 2, 3, 4, 5, and 5-membered rings are very stable. So a 5-membered ring is generated. Now once this 5-membered ring is generated, I'll show you the product. That will be easy. So we have a 5-membered ring generated like that. Okay, and over here we have a or I'll just show you what will happen. So if a 5-membered ring is generated, what will it look like? So 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Okay, and then we have the 5-membered ring. Oxygen, double bond O. Then we have this. Then we have a chlorine over here. So this is generated. Okay. Now we are adding trimethylamine. Trimethylamine is a very weak base. So the most acidic proton present over here is proton on this hydrogen, right? This is the most acidic proton present. So this NET3, this base, so this base is going to abstract this proton, and this bond is like this hydrogen is going to form alkene, and this Cl will leave to give us this product. Okay, so this is the mechanism for this reaction. Now this is a very good example. I'll repeat again, sorry for the bad drawing. This oxygen is protonated by H plus to form oxonium ion. This lone pair on the oxygen attacks this double bond. Okay, so this bond migrates like this, then comes back, and then it kicks off this ethanol, and we get ethanol as the byproduct, and this 5-membered ring is generated. Now this triethylamine is a very weak base. It abstracts the most acidic proton, which is this hydrogen, this one over here. Why is it the most acidic? Uh, because why is it the most acidic? Because it is next to a carbonyl group. Just a minute, I'll show it to you with another color. Yeah, so because it is next to a carbonyl group and it is also next to a chlorine, so both are electron withdrawing groups, which make this hydrogen very acidic. So this abstracts this hydrogen and we get the product over here. This case, this is the product. This oxygen is below the plane, this one over here, this oxygen is below the plane, this hydrogen is above the plane. And what about this? This is a pretty simple reaction. If you know this methyl chloride, what is a methyl chloride? This is a, these things you should know. What is methyl? Methyl is CH3S. This is a methyl chloride. S double bond O Cl. Okay, so it is basically it it reacts with this OH. Okay, it reacts with this OH, and once it reacts with this OH, and by the way, just a second, in the previous question, when this triethylamine attacks the proton, a negative charge is generated over here, then this negative charge migrates to kick off the Cl, right? So it is also going through E1cb mechanism. It is also going through E1cb mechanism because the negative charge is stabilized by the carbonyl group over here. Okay, because this double bond can this bond can migrate like this and form O minus, so it is also stabilized, so that is why it is a E1cb mechanism. Now what happens is this methyl group is a good, it makes the OH a very good leaving group. How? Because if we have lone pair on this oxygen, right, we have lone pair of electrons on this OH group, this oxygen attacks this sulfur, this oxygen over here attacks this sulfur, and this Cl is kicked off, and what is generated is a O methyl group, right? So this OH is converted to OMS. This OH, if I remove this hydrogen, is converted into O methyl. Now this O methyl is a very good leaving group. O tosyl also you must have heard of. It is represented by TS. O tosyl, O methyl. These make the hydroxy group a very good leaving group. Now this triethylamine is a weak base. So what it will do is it will abstract one of the protons. Let's say it abstracts this proton. So this triethylamine abstracts this proton over here, and this OMS group is kicked off. Okay, and so what is the product that is generated? This group. So basically nothing is happening. One of the one of the hydrogens is abstracted by this triethylamine amine group, and it leads to the formation, and O methyl is kicked off, and this product is formed over here. Okay, so I am sorry for the writing, but I think I have made the concepts clear. I have been been vocal about what I am doing. So even though the drawings are not correct or not good, but yet I think you would have understood what kind of reactions are taking place, right? So sorry that I couldn't make it on the whiteboard because I'm in the laboratory and I do not have the time, so I decided to make on this. And if you like my videos on the slides, just please comment down below so that I might invest in a graphic pad, so that my drawings are better. Instead of writing with the mouse, I'll then start writing on the on the graphic pad or on the tablet. That will make my writing better. So just comment down below if you like my videos on this slide, and then definitely I'll invest depending on your response. And please like and subscribe to my channel. Thank you.